Hello and welcome to the Go for Ruby developers session, where I'll be describing different concepts in Ruby and Go. This requires you just basic OS level knowledge, and some Ruby knowledge is plus, because this is really oriented towards existing Ruby developers who are seeking for quick onboarding to learn Go. So my name is Lukáš, and I've spent about 10 years on a huge Ruby on Rails code base, and I have past experience with Java and Perl code bases in the past. And I use Go for my pet projects from its beta version, and I'm a huge fan of Go. And our team is recently moving towards a new Go-based, microservice-based architecture, and we have a lot of great Ruby on Rails developers, so this session could be helpful to sort out some thoughts about how and actually why Go is designed in a way that it is designed. So I watched about hundreds, maybe 200 talks about GoLang on YouTube. And so basically this is a collection of thoughts from these talks and maybe some documentation, a little bit of my experience, although I'm not that experienced in Go yet. There's a nice talk by Kaylin. I think it's called Go on mainframes. And they were building a new team with people with different language backgrounds. And she observed that people coming from different worlds and languages struggle with different things or parts of Go, and it's something that struck me was Ruby and functional people struggle with pretty much everything, which is interesting and kind of confirms my thoughts. Is that Go is different, really. If you're a Ruby or Ruby on Rails developer, Go is very different, and it is exactly the opposite of Ruby in many ways. So just a quick recap: Ruby is an interpreted high-level general-purpose programming language, object-oriented. That's the major design, and was released back in '96. While Go is statically typed compiled programming language with some features from dynamic languages, things like type inference, fast compilation. So it almost feels like an interpreted language, package management. Versioning and things like that, and duck typing or structural typing in Go. That's the term, and these things are really something that were or are a thing in 21st century. And Go is from 2012 actually, so it's much younger. So for this reason, it has a lot of things designed in a way that it's great for these days. So by the original Ruby author, the design principles of Ruby is he wanted a true object-oriented language, mainly as a scripting language, and best features from Lisp, Smalltalk, and Perl. And it's really openness is the key here. It's open to new features. The language is open to be extensive. Libraries can do manipulations of things in even in the kernel module, which is like the root context, the built-in functions and things like that. And that's design, like be extensive. Go, it's very different. Like its design principles are very different. It's built on top of a minimal possible set of features. And this is very, very important to the original authors of GoLang. Static typing and runtime efficiency, readability and usability, and high performance and networking and multiprocessing are the key features and key concepts. Everything really revolves around these key principles. And Rob Pike, one of the designers of the language, like to say that, if you bring a lot of great features from great languages, you end up with a pile of features, right? It's not that uncommon to create a language which has so many features that you're actually overwhelmed with them, and that's not what they want to do. And it's okay, maybe things like Java, JavaScript, C#. That these languages are bringing in the features. What's different about Go is they don't want to do that. It never happen. It will never happen actually. Or he likes to say like the design of Go 1 is final. Like we're not adding anything like major here. It's done, and just go ahead and use it. There's also a version promise that Go 1 will always stay compatible, so people can just build their services, their software. And actually, there were some talks about Go 2, and one of the major features that could be in Go 2 were generics. But this is actually changing. Like a week ago, or actually this week, Go 1.18 was released, and it actually has a backward compatible implementation of type generics. It's not called generics. We'll talk about this a little bit in this session. So these are the major principles. So I did some research, and I actually found out that in its 26 years of history of Ruby, about 20 major features were added to the language. That's approximately 0.7 major feature per year. Now, in Go, it's actually incorrect now because the 1.18 came out this week. We have one major feature in its 10 years history. I think everyone agrees that generics is a major feature, and all other small features that were added were not that big. Even packages, modules, that was like not a huge deal. It was just a new tool within the language, although it's built in. And so yeah, that's one in 10 years kind of things you need to worry about. One in 10 years, a thing that you need to learn. So that's also a thing to consider. Now, I won't list all the features of Go. We'll go through them during the session. However, I can list features that are not in Go and won't be. Things like implicit type conversions. That's always explicit. You need to do type conversions yourself. Assertions are not there. You can't do assert if a variable is nil or 1 or any kind of value. You can do type assertions, but that's a different thing. Inheritance, there are no classes, there are no inheritance. Points of arithmetics and other things are not in the language because readability is key. That's one of the major design thoughts about that. Installation of multiple versions. So installation of Ruby, just install Ruby using because Ruby is a major language. You install it on macOS using Brew, on Linux using package management. That usually gives you a good version to start with. And if you want to switch between multiple versions or among multiple versions, you do use one of the world famous libraries like RVM or RBNF. I've been using RBNF. It's a little bit more simple. So you just use RBF. There's an install plugin, so RBF install version, and then set this version. It will just download and automatically compile Ruby from its upstream sources. And it's a great tool. That's something that is really good in Ruby, and GoLang actually has something very similar. So installation of Go is also simple. You just grab a package for your Linux distribution or use macOS Brew. However, and there are also installers for Windows and macOS and Linux, binaries, official binaries. And that's what I would like to actually suggest, because now I'm on Fedora 35 and it has Go 1.16 because 1.17 was, I think, released just before Fedora beta or something like that, so they couldn't finish and meet the targets for Fedora. So it's 1.16, and 1.17 is, for example, for the project we'll be working on. I already tried a example application, and that one requires 1.17 already. So what I would suggest is install 1.17 or 1.18. Just like that, download the binary and just extract it. The user local Go is the extraction point in this case, and then add this to the path, and that's all you need to do. GoLang, one of the key principles in Go is by default it compiles in a static binaries, so you don't need to actually do you don't need to battle with libraries. It has some benefits. That's obviously a huge benefit. So you have a binary and just pick a correct architecture and it works. It has some drawbacks, like security people don't like that, because on Linux it's very common that you have a distributor like Red Hat, that's my employer, and then you come to them and say, hey, this is like there is security vulnerability, and we fix that for you. Or somebody else found something, and we Red Hat in advance prepares patches and releases updates for all the packages, and then the security team within Red Hat is able to track down all the libraries of we have, all the things that needs to be patched, because everything is installed from RPM packages. However, here is not. It's a challenge, and it's something that Red Hat's actively working on, and I think we have a great progress in there. So there are tools which can actually inspect binaries for security vulnerabilities, including GoLang binaries. So as you remember, I was talking about RBN for Ruby. There's actually maybe a hidden feature a little bit of Go. You can actually install a package called Go 118, 117, so Go and version without space. You just use the latest, because the version actually of the package is not used. It's in the name of the binary of the package, and it will actually drop a binary called Go and version without space. And if you drop, if you have a home folder, the Go folder in your path, which is typically what you do when you're installing Go, you just type Go and the version number and download. And this I think it's a stub, and because it's very easy, fast to download and install. So it's just a small, like kind of a script more than like a big binary. The download command would actually download Go, and it will go into your home directory SDK subdirectory. And in the SDK, you'll have multiple versions of Go you can use. And from now on, you can use Go 118, build some, or Go 118, whatever tool you want to use. However, this is kind of a limited, I would say. I have never used it. I just learned it the other day when I was learning about Go installations and paths. So there are tools like GoVM or GoEnv, which are essentially like counterparts for Ruby world or for Python, PyEnv and things like that. So you can use that as well if you prefer. But I just wanted to drop a comment on that's also an option. Cleanup is very easy. User local Go bin is the correct path. I think there is a typo there. And home Go and home SDK if you install the multiple versions. Otherwise, SDK is not present. Is what you want to delete. In the home Go folder, you'll find all the packages, compiled libraries, and also binaries. If you install a Go package that provides a command, for example, that will go into home folder /go/bin. You can change locations of these, of course, using environment variables. But I think this improved a lot with Ruby, with Go 1011. You kind of had to have a Go path and Go root and things like that. It was more complicated. I didn't like that. And with the changes through the whole Go lifetime, it's just now very, very good. It's just you have a directory, 2 directories perhaps, or 3 if you install different versions. Now, types. Yeah, so Ruby, we don't have types actually. There are no primitive types. Everything is an object. So fixed num is an object, big num is an object, string is an object, everything is an object. So you call methods on objects as well. So you can type things like 1.2s, like convert fixed num1 to string and things like that. Although Ruby 3.0, I think a year ago, or 2 years ago, time flies, I'm not sure, actually introduced RBS, a new type system, which is kind of a metadata annotation type system, which will help you. So your IDE will actually show you some types and maybe enforce them in some way. But that's something that I haven't seen widely adopted yet. So hopefully that will change. For bigger, larger projects, this will be a godsend, I think. We'll see how it goes. So GoLang has types. That's very new thing for you if you have never worked with compiled languages. Everything needs to be some type. So we have this following basic types. I won't name them all, but Rune is essentially like a UTF, Unicode character, which can be 1 byte, 2 bytes, 3 bytes. Then we have also ints are unsigned integers, so we have signed and unsigned variants. Of course, unsigned start with 0. And that's pretty much it. And we'll have a pointers, arrays, and maps. We'll talk about that later. So this is how you declare variables in Go. Important thing, and that's something that's when I'm writing new code, my brain automatically switches to C. I've done a little bit of C in the past, and I just declare variables in a different way. The int I, so in C, type goes before the variable name. Here in Go, you just say var, that's a language keyword, the variable name, and then the type. Go actually ensures that values are nullified. So integers are 0, floats are 0, strings are empty strings, and booleans are false. This is guaranteed by the compiler. And to assign variable, obviously that's equal sign. If you want to group variables, you use this special syntax. It's a parenthesis, that's not a curly brace. So it's not like a block of code, it's a block of, or group of variables. So this is how you do it. Also note there are no commas. The syntax of Go tends to be like, you want to write as little things as possible. So you'll see this in a bit that things are pretty simple and nice to read. Yeah, so that's a variable grouping. So very important thing is type inference. So in C, if you are coming from C, maybe, although this is talk for Ruby, I know I'm referring to C because I did some C before, I shouldn't do it perhaps. So in C, you just always declare a variable, like this needs to be integer, so that's gonna be int. In Go, what you can do is actually, if you have a number 1, which is like a constant number, the compiler actually knows like this is an integer, right? So it will actually infer the type here, and inferring needs to be explicit. You need to say colon equals. And so in the first case, an integer will be a variable of type int. A string, a variable name, will be, or variable will be actually string type. And compiler will do this in the background for you. So this works nicely. And this is kind of a, here Go is more approachable for those who are coming from the Python and Ruby and JavaScript, for example, because it feels like, you don't need types everywhere. They kind of work. But then if you try to pass an integer here, a variable, into a function that only requires the argument is string, you'll have a compile time error. Pointers. Don't be scared if you don't know what pointers are, or if you haven't worked with pointers in the past. So pointers are essentially like references to a specific memory location. You declare pointers using var and then pointer name or variable name, and then star and the type. So you always need to have a pointer to specific type, although you can have pointers to empty interfaces, but here, just let make it simple. So we have a pointer to specific type. Go runtime or language compiler will ensure that this is nil by default. And then here I have a variable int I, which is 42. And then if you want to grab set a pointer to specific type, specific address in memory, you use this ampersand syntax, which is ampersand I. So into P1, I'm storing an address of int variable, which is, by the way, 42 right now, to pointer 1, P1. You can, of course, the type pointer inference works the same way as on normal types. So P2 can be also like a pointer to I, and this will be automatically created the compiler will figure out that this is actually p2 is actually a pointer to int, because I is int, so p2 is pointer to int. And to dereference a pointer, so if I have a p1, if I were to print the variable p1 to the console, I would get like a long number, like an address in memory, because memory is virtual, so you're getting big numbers on 64-bit architectures. These are 64-bit numbers. If you want to dereference, like you want to actually see the actual number, the integer, the number to 42, you need to dereference the pointer, and that's the star syntax. So you put a star before your variable name, and the compiler will do the dereference for you. Of course, p2 is also the same pointer, so you can do the same. So this will print 42 and 42. Now here's a snag. You can do pointer arithmetic. So in C, again, I'm doing this, sorry, but in C, pointers are like essential. You do a lot of pointer arithmetics there. So you can point to memory and then move the pointer around, you know, anywhere pretty much. And that's very dangerous, because if you move pointer to some location of memory which is not valid, it's perhaps even not yours. No, the process kind of doesn't own it. Or, I mean, in this case, because memory is garbage collected, so it's the Go runtime does all the memory allocation for you. You would actually point to something that could be even deallocated. So you can't do it. This is not allowed. So if you try to do p1 plus 32 or p1 plus p2, that's always a compilation error. You can't do pointer arithmetics, and this is safety. Like GoLang authors didn't want us to do nasty bugs, and that's great. So naming conventions in Ruby, like if you have capital, that's it's actually a constant, but class names are still constants. So you use camel case for class names and underscores for methods and variables. And constants typically are all caps. Now in Go, it's a little bit more simple, I think. This is not like for local names, variables, and types and functions. You use this. It's not a camel case. I think there's a term for this. Just the first letter is not capitalized, and then you don't use underscores. You just use for in every single word a capital letter. So that's what you should use. This is not enforced by the compiler or anything like that. So you can use underscores if you want, but that's nothing you should probably do. And now if you want to export a function or type, and I'll talk about exporting in a minute when we'll be dealing with packages, you just start the name with capital letter. So comments. In Ruby, we have a single line comment and multiple line comments, and the multiple line comments are actually not that widely used, typically. And these are very often used for commenting out some portions of code sometimes, but you can see them in use as well. And Ruby has some kind of a documentation DSL. It's very common, and Ruby community is very good in documenting stuff. For example, the Ruby on Rails, one of the biggest libraries ever in Ruby, that's very well documented, I think. And the tool is called RDocs, which will generate you HTML and pages and PDF pages, PDF documents and things like that. In Go, it's kind of similar here. We have single line comments, which are people are encouraged to use them everywhere. And the GoLang community landed on using the multiple line code blocks command for actually commenting out code blocks rather than doing comments. And you'll see this a lot. In Go, it's very common to have short, small interfaces, short packages, or rather short functions. And these have also short comments. That's what I observed from the main Go library. And actually comments are essentially like a text. There's no special syntax. You just describe what you want to tell. The first sentence is special. Things like Go tool, which is built-in tool, which basically allows you to print documentation of any package, function, or variable within your whole installation. Or it can also spawn you a server, so you can use your browser to browse your whole library of packages you've downloaded. It shows the first sentence as like an overview. I think it's on the index portion of those pages or screens. So you want to ensure that the first sentence is like describes what it does. It also, there's a recommendation if the method is called, in this case compile, the first word should be compile and then blah blah blah, and that's the recommendation I've seen for some reason. So I think I'm okay with that. And that's about it. I mean, I remember my Java days, when you implement an interface, you're getting like 20 methods to implement and 20 Java doc comments that require all the parameters. And this kind of always was like name and colon. That's a name, right? Like what you can document about an argument called name, right? It's a name. So I think like this approach is good. So constants, as I said, are capital letters. They need to start with capital letter, but typically they are all caps. However, there's one little detail. Actually, constants in Ruby can change. They are not constants, which is weird a little bit on the first sight. But actually, like Ruby is different. It's meant to be extensive. So this has it has a reason. It's a not bug. It's a feature, and they are not changing that. So you just need to keep this in mind. I've seen a lot of these already uninitialized constant during my time with the project, and every time we fixed few and we saw another bunch, and yeah, so it's not error, it's warning when in Ruby. So in Go, these literally are constants. It's also because they are allocated in a portion of memory, which is, I think it's read only by default even, and one particular thing, so there's nothing special about constants. We have this keyword that's the syntax. However, in Go you don't have enums, and that's actually similar with Ruby. In Ruby you also don't have enums. There are several techniques you can use in Ruby, like use modules, use constants and things like that. And in Go that's similar. Like you define constants, and typically like warning is 1, error is 2. This kind of constants. There's this special syntax, like there's const block. Again, that's a parenthesis, and this, I'm not sure how to pronounce iota keyword. This is like giving you like something like a sequence in SQL database. It gives you increasing number from 1. I think it starts with 1 or 0. I'm not sure. So warning will be 1. I think 1. Error 2, and then the underscore. This is like a little trick if you want to like reserve number 3 here. Just use underscore. Underscore is in Go is used for a variable that's you won't actually use, and it's very important because the compiler will actually enforce this. If you create a variable in a function and you want to use it, the program won't compile. The compiler will insist on removing this variable. That's can be sometimes like a little bit awkward, but it is what it is. Again, the design, one of the major designs of Go was like to keep it very fast to compile, because Go was actually invented in Google or at Google because they were struggling with their huge C++ and Java code bases, and I've heard Rob Pike saying like one of their projects were compiling for an hour. And with Go, it was like 3 seconds and compilation. When they translated that to, actually they have, it's weird stuff. It's like crazy. They have translators from various languages and things like that. And yeah, so that's interesting. So these are constants. Printing, yeah, we have putc. That's a nice feature. It's like putc is very short to type, and you do a lot of putc fairly often. Although in bigger projects you have a logging, so just like do log debug, and so it's not that short. But for scripts, that's great. There's also printf. These are like kernel kernel module methods, so it's like built in. In Go, you have, okay, so it's a little bit more complicated. You have built-in functions, print and print line, but these are not recommended like for, should I say, like production use or like final use. They all print to standard error, so that kind of already shows you that these are meant to be more for like debugging when you want to quickly print a variable and something like that. And they actually reserve the right to actually remove them in the version 1 of the language. So just use them for like debugging, but don't commit these into Git or into your SCM. For printing, like normal printing, you should use FMT package. You'll often see package names are very short because this could be format. But since you'll be typing FMT quite a lot, or format, this is again one of the design principles of Go or idiomatic Go. And there is also a book called Effective Go, which you should definitely read. It's very short and gives you a nice overview of what you should do, what you shouldn't do. So package names should be short. That's also a recommendation. You can import a package under a different name, but that's not what you want to do unless you have a conflict. So of course we have a printf, fprintf, things like that. So and everything works as expected. Similar to Ruby printf, you have this syntax, dollar syntax, which comes to it's very same as in C, right? Okay. So structs, very important topic. I think in Ruby we don't have structs at all. You just use classes. There's open struct, I think, from the standard library, but that's again, I think it's a hash actually. So the Ruby don't have structs, which is a little bit shame. Which is a shame because structs are very efficient. So struct, if you are not coming from the C background, it's a user-defined type that allows to combine other types into a single type. One warning, they are subject of memory alignment. So this is, I don't want to go into details about this. However, it is important to understand that on many platforms, including Intel, there is a thing called memory alignment. And that's like a performance optimization when some addresses of memory can be accessed in a faster way. And all you need to remember is that if you're, for example, doing a struct which has a boolean and int64 on a 64-bit architecture, you should probably order the struct because structs are saved in memory in the specific order, in the same order that you didn't declare them. So here we have x and y, both are integers. By default, integer is 64 bits. And by the way, there's also a type called int64, and if you just use int keyword, it will just use the int64 on 64 platform, which is Intel 64 typically, or ARM 64, right, these days. So this is okay, but if you just like have a boolean is a byte, so just like 8 bits, you should your struct should be in order int64 and then the boolean. So that's more efficient than if you do this the other way around. It can be a little bit slower to access the boolean or to access the struct. Sorry, and there's more about that. I don't want to go into details, so you can read about this. Just keep in mind that the order matters, the way how you declare your struct, and not in this case though. So here we have struct, there's the syntax, and the new keyword creates a new variable of the struct type or the vertex type. All the members or all the fields are guaranteed to be 0, so x will be 0 by default, so you can set them to 1 here. There are no constructors actually, so there is nothing like constructor or destructor if you're coming from C++. Or from Ruby we have initialize, right? We have a class and initialize. That's there's nothing like that in Go. So you might ask, like, how do I initialize my struct? So you just create a function that, you know, it can be called initialize, or like typically it's a new with capital letter. So new, whatever, new vertex, you could write such a method, but you don't actually do that a lot, because there's a syntactic sugar here. To create a new variable of the vertex type, you just use this, you just use the type name and then the curly braces, 1 and here the order matters. So like xy is the order of within the struct. So that's how you want to initialize the stuff. And I mentioned the memory alignment because it's actually can be hard. It can be a lot of work to actually change the order if you do it incorrectly from the day one, because then you need to change all these statements. Of course, structs can have also, there can be pointers to struct just a little bit. Apologize, I'm back. So yeah, you can have pointer to struct as well. Now, interesting thing is dereferencing. Accessing fields. V is a vertex type, so that's v point, and the point is actually the dot is the way how you access fields within structs, and p is actually point, and you can tell, like typically in C you would do dereferencing with the star. But here the Go compiler will actually figure it out. Like it knows that P is a pointer to vertex, and so you can just use dot the same way as P was actually the type itself. So that's a nice thing, and it works like naturally. You just don't think about it, which is great. So getters and setters in Ruby, we have those. In Ruby, that's actually getters and setters are implemented in a way that there is actually possibility to override the equal. So you just do that. I don't have a slide for that, and so it's built in Ruby. Ruby has getters and setters nicely implemented. In Go, however, the thinking was like, let's not make the language complex, just use functions again. So here we have an attribute name. It's not an attribute, there's no such a term in Go. So we have a name, and so name returns name, and set name sets the name. That's the recommendation. Like, you can implement pretty much anything, but this is what you will see in a lot of libraries. Arrays, so these are in Ruby fully dynamic. So you create an array, it has length and capacity, and you just put the things into array, and you can extend the array very easily. That's how it works. In Go, it's different again. This is something that you might struggle with. We have arrays and slices. Arrays are much like a C arrays. These are fixed size arrays of a type. So here we have a array of 40 strings, and the array has 32 elements. Actually, or if you have an array of integers, these strings are actually pointers to, so the compiler already, when creating array, compiler already knows the length, so it can also optimize that memory wise. And you can actually extend the array. If you have an array of 42 elements, you just need to create a new array of 50 elements and copy the contents. Which, you might think like, that's weird. Why would I do that? Like, arrays are very effective when you know exactly how many things you'll have. And maybe you're implementing a ring buffer of 1K elements of some kind, or pointers, so you can create that, and this will work just fine. Now, if you want to work with more of like Ruby arrays, you have slices. Slices, you can tell a slice you can tell how to create a slice, or if there's a slice already, that the slice don't have the number in the square brackets. And you can create it using two syntaxes. The first one and the second one. The second one via the make. It's very common, and make is actually it's a special function, built-in function. In this case, it creates a slice of ints, 64-bit ints in 64-bit architecture with a length of 5 and a capacity of 10. And make actually differs from new in a way that, because why we can't use new? Because new doesn't actually do initialization. Slice is actually, and we'll see this with hash, is a more complex type. It's built-in type, so it's more complex. So make actually does perform some kind of a constructor or something like that. So that's why we use make. And you use make for maps, slices, and channels. And then when you want to enlarge capacity, then you use a built-in function called append. Okay, and one more important thing is to realize that arrays, not slices, but arrays are actually values. So they are passed in as a values into functions, or they're, if you assign a new array, it's actually a copy. So the compiler will copy the array. If you want to pass array without copying into function, you can use pointers. So Ruby has hashes, and Ruby has hashes everywhere. You'll see hashes all around. And that's the syntax, and nice thing that illustrates how difficult things can be in Ruby is when I was researching and I searched for how to delete a key from a hash, I landed on Stack Overflow, and then the verified answer was like, hey, and the question was, how do I delete a key from hash? And the answer was like, hey, use except from Ruby on Rails, right? So this illustrates like how Ruby is kind of everyone is expected to be using Rails, like 80% maybe of all the code is Ruby on Rails, perhaps. I'm not sure. I just made this up, but and it's kind of it's not actually the correct answer. Correct answer is delete. Delete is a built-in function within Ruby. Deletes element from hash. And by the way, those columns, these are called symbols, because symbols are actually optimized in memory. These are just basically like numbers or constants, which might be like, yes, I want to optimize, so use symbols everywhere, but it actually creates a lot of bugs, because a hash or key, which is a symbol called symbol, and a string symbol, these are two different keys with two different hash values, and you'll see a lot of problems. Of course, we have hash with indifferent access, which is again Ruby on Rails only library or special class, but you'll run into many issues with that. Now, by the way, the answer use except is not actually, well, it is correct, but the except will return a copy of a hash. So except bang is what you want to perhaps use if you're on Ruby on Rails, or delete without bang. By the way, bang is convention that is widely used within Ruby on Rails, but not in Ruby. It's bang means that the method has a side effect. It is expected to change something on the instance. So hashes, we don't have them in Go. We have maps. Maps are very much hashes, except they are typed. So you just need to declare. So again, I'm using make to create a map, because it will need to initialize the structure in a way. So we have this square bracket syntax. So map, and keys will be string, and values will be int. And the moment you'll try to store a string into this as a value, you'll have a compile error. The moment you try to use let's say int as a key, again you'll have a compile time error. So everything is typed. Of course, there is a special type called empty interface, which is literally you write interface and opening and closing a curly brace. And there's actually in 1.18 there's a new feature. So like a few days ago we have any, which is actually empty interface. So you can use any now. So you can actually create maybe a map where string with string keys and empty interface, or which is any as the type. And in that case you can store anything pretty much in the hash. However, you need to you do type assertions, which we'll talk about later. So accessing keys, again, it's easy. However, fetching from hash, from map, is different. You have two actually values, the value itself and boolean, which tells you like true or false if the key, if the value was there or not. And this is different, and you can just, this is how you use maps. There's no other way. And I think this kind of fixes the problem of like when it returns a nil. Was the element there and was nil, or was never there? That's the way around it, and I think I like it. Although you'll need a little bit more code every time you access something from map. And delete is the built-in function that deletes from map. So now let's talk about functions. So functions, yeah, there are methods in Ruby. Everything is a method, everything is an object, and objects have methods. That's the syntax. We very often, Ruby programmers very often don't write return statement because everything is a expression in Ruby. So x and y evaluates to x and y, which the last line evaluates to, that's the return value. In Go, it's a little bit different. We have functions, we don't have methods, although you can refer to functions as methods sometimes. These are functions basically. And yeah, we have this syntax. One thing again, when I'm switching, my brain switches to C mode, the variable name goes before type. So X string, Y string, Z string, not the other way around. And if you return just a single value, just then you don't need to use the parentheses. But if a method returns multiple values, and it's very common to see functions to return multiple values, you'll see this syntax with parentheses. Important thing to understand is function overloading is not possible. So you can't create another function called swap that will have like a one argument or two or three arguments or two arguments of a different type. That will result in a compile time error. So that's something, again, authors of Go aiming for simplicity. You don't want to do that. You don't want to allow that. So here, that's an interesting thing. Optional and named arguments. You know, in Ruby, this is like essential in Ruby, and I think it's one of the biggest complaints I have against Ruby for a larger code bases. Of course, Ruby can't be Ruby without this. Like you have args and quarks. So if you don't know that the args is actually array, that's like optional arguments, and the quarks is actually you can pass hash into a method, so you can actually call the method with multiple arguments, and also you can pass named arguments like a quark, and it will work. It will just args will be array, quarks will be a hash, and you can access them within the method context. There's a new thing. It was added, but I think in 2.7, 2.6, I'm not sure. These are called named arguments, and this is like a real syntax to do naming of arguments, and it's and you can actually mix and match these together. In a way that it's a source of bugs. I have only recently merged a fix within our code base. It is what it is. But it is, this comes with a cost, like things, when you look at a method in Ruby, you sometimes not only don't have types, you don't actually know what the method actually is, what the method actually wants. You don't know the arguments, you don't know like the options or extra arguments. So named methods, named arguments may solve this a little bit, hopefully, but it's a mixed bag. But again, Ruby is Ruby. That's not bug. It's a feature. You couldn't do any kind of DSL without this, right? So in Go we have variadic. I'm not sure how to pronounce that. So that's essentially like an array of type, a single type, and that can be seen as variable arguments. The syntax is 3 dots, and it needs to be the last, of course, argument of a function. And that's how you use it. It's pretty straightforward. If you want to convert existing slice into variable arguments function, you just use the 3 dots on the right side of the expression of the variable name instead of the left side. So that's the syntax. So Go don't have many built-in functions, and I like that. I really think that it's important to have like a clean root context. You don't want to have many functions, and it's pretty clear that the Go team, the language designers team, was aiming for like to keep this as clean as possible. And print and print line are actually used just for like debugging purposes, like printing to standard error. So it's actually less than that, and it's not much actually. Like, and we'll touch a little bit of almost all of them. Like len is len and cap is for length and capacity. That can be used for arrays and stuff. Make and new, we've seen them. Panic and recover, we'll talk about them in a bit. And print line, and then we have image. So where's that? Imag and real, that's for complex numbers. And we are left with append, which is for appending to array, and delete, that's deletes you from a key from hash, and then we have close, which actually I'm not sure what's that for. Close is a file handle, and that doesn't sound right. So I'll research that, or drop me a comment if you can fill me in. So in Ruby, as I've said, everything is expression. So it's very common to see like def1, that's the return value, and that again, it's a feature. That's how Ruby is designed, and because then you can, without this, you couldn't do pretty much any of the DSLs. DSL is very common in like domain-specific languages. And so, and the whole like active record within Ruby on Rails is basically built around that, or migrations and things like that. So everything is expression. In Go, that's different for Ruby developers. You'll be a little bit torn, or a little bit bugged with this, is that the compiler will insist on statements and expressions. So some things are statements. By the way, a++, that's like increase the variable by 1. That's actually a statement, not expression. In C, it's a statement expression. In Go, it's not. So we just need to like you can't, like that limits you a little bit. If you're coming from the C, you'll find like sometimes writing this and expecting it, but the compiler will quickly tell you, no, that's not gonna happen. And some expressions here, we have a function as an expression, and numbers and things like that, like mathematical expressions, of course. And function call can be used in both contexts. But the message here is sometimes you'll need like 2 lines instead of 1, and that's the design of language. Don't like expect it to be changed. So Ruby, everything is an object, right? Constant is an object, module is an object, one is an object, circle is an object which inherits from shape. In this case, it has a draw methods. That's like Ruby is object oriented. That's how you design stuff, write stuff. In Go, we don't have classes. We don't have any classes. We do have like, there's nothing like an object term in the maybe in the Go language specification mature, but you can refer to things and variables as to objects. That's fine. So here we have a variable type points, which is struct. We already know what struct is. X and Y is a float, and then we have a circle, right? And in Ruby you would see it like, okay, so point is a class, circle is a class, and maybe I can, like, circle is a special kind of point, although this is kind of weird example, but you could do it. You could inherit a circle from point and add a radius, things like that. In Go, however, what you do is composition. Composition is an object-oriented technique which can be done pretty much with any language, and even any object-oriented language. It's like inheritance is very often overused. You very often see classes which inherits other classes, and you could achieve the same with object composition. And composition is built in the language in Go in a way that you could actually create a circle which has two types, point and radius, and you could just do it just fine. But here you can embed actually point into circle in a way that when you create a new circle variable, you can actually access X and Y and radius directly, like if this was actually like the same struct. So that's called embedding, and you'll see this a lot in GoLang code bases. You can also embed pointers. So here we have a read writer, pointers to read, pointer to reader, pointer to writer. It's also common. So yeah, as I've said, composition is possible without embedding. So note that here in this case, if you're doing like a composition without embedding, you need to type a variable name or field name. So here we have reader and writer, which are pointers to reader and writer types. But then, the implementation needs to do like the forwarding. So here we have a read methods or function, and that returns like RW is read writer. We'll dig into the syntax in a bit. So you need to the point to take away is that you need to dereference like the field name, like rw.reader.read. That's how you like forward this to the field, to the composite structure. And then you can sometimes see a mixed embedding. For example, here we have a job that has embedded logger and not embedded like regular field command. So here you can see the difference, like job command, you access that directly, and job logger, you don't. I might have that incorrect. That's could be actually the other way around. I haven't tested this one, I guess. So it might be the other way around here. I need to take a look. Drop me a comment if that doesn't work. If you have by the way, you can go to play.golang.org, which is a wonderful Golang playground where you can actually test all, like 99% of all the Go language works. There are some, of course, constraints because the things you actually execute were actually run in the Google data centers, and you can, of course, do things like maybe write a Bitcoin miner and run it there. Of course, that's not going to happen, but or open files on the disk and things like that. But you can actually test very easily. It's very fast, very very nice. And then go ahead and also use read. And if you haven't tried this yet, I highly recommend the Go tour language tour. Which uses this technique, this technology to actually show you examples, and it's asking you to fix some things and things like that, so you can test your ideas as you learn the new things. So here we have methods and we have attributes here with a at character. So this is how Ruby looks like, and that's what we actually as a Ruby programmers know very well. Now in Go, as I've said, you don't have methods, but you can create like functions on objects. You can refer them as methods. I think they are referred as methods in the documentation as well. And the way it works is that you have a type. It can be struct or it can be any kind of built-in specific type, like int, just integer. Here we have structs of string and int. And then you create a function, and with the parentheses, we have a funct keyword and parentheses. That's actually a thing called receiver. So you actually are declaring receiver here. So it's p person, and then the function name. Everything else works the same way. But in the context of this function, name it r, name it h, you actually have a p variable, the receiver, you can actually refer to. So you can access p name, ph, and do pretty much anything. And then the way it works is you create a new variable of person. Again, we are not talking about instances here, but maybe you can say that. It's okay. We'll understand. So person Luke 42, and then to access this function or method, you just call p dot and name with h as you would expect. Note that the parentheses are required here. It's not just in Ruby you could run away with a name with h without the parentheses, but in C you just have to do it. It's just how you call functions. You could name this as self, so to have this closer like to Ruby, but don't do it. The recommendation is to use the P for person and N for name. Shorter, typically shorter, or even single character are very common because you'll use that a lot. And you could actually, so the compiler actually does this, and it's syntactic sugar because you could actually do the same thing without this syntactic sugar. You could actually use the receiver as the first argument of methods, and that's for example how you write object-oriented code in C. If you ever worked with the G-object library, which is very common in GNOME project, that's the way how it works. And you could do this in Go, but why not use this syntactic sugar, right? Again, the type can be just also primitive type. It doesn't have to be struct. It's important to understand that a receiver is a copy of, it's a normal argument. So although it has special syntax, it's a copy. So when you have a like person here, and you want to actually modify the person, so you want to actually have a, in quotes, like method that, for example, increases the age by 1, you actually have to use a pointer to person, because then if you wouldn't do this, if the receiver was p person without the star, so it's not normal type, it would actually increase this by 1, and then the variable would disappear from stack, and nothing would be increased. And again, to call a method or a function on a specific instance, again in quotes, we don't use that typically, like it's a variable. You use this dot syntax. Again, you don't need to dereference this. This is like, again, some syntactic sugar, and it's nice. It works very naturally. You don't think about it anymore, which is great. If you're coming from C or C++, was always like, oh, I have this error because it's I need to dereference. Well, in C++, it's better, but in C, in C there are no classes. In C, if you're doing G object, then you need to take care of everything. All right, so that's called pointer receiver. So abstract classes and interfaces, so Ruby don't have abstract classes. Abstract classes actually don't make sense, or even interfaces, because Ruby is fully dynamic. You have a little bit different concept, which are called concerns, and you include and extend modules quite a lot. So it's nothing like you are missing those in Ruby, although sometimes abstract class of some kind. Maybe we're doing it wrong in our project, so sometimes we have these classes which do nothing, and throw an exception if you call a method. So in Go we have interfaces, and this is the syntax: type, name, and then interface. And Go runtime has a polymorphism, and it has structural type, and the compiler knows the compiler actually implementing the interface is automatic. You just create a function on a type that matches the name and all the arguments and return type and everything, and the interface has been implemented in this way. You don't need to actually write implements interface, just like in Java or C#. This is also known as duck typing in Ruby, although in Ruby it has a little bit different, context. But the idea is the same. And in Go, it's very typical to have small interfaces, which typically has a single method, single function. So the interface is just a list of one-on-one methods. And again, they are implemented implicitly. So here we have a geometry interface and rectangle interface, and then we have a function which has a rectangle as receiver area. We have a rectangle struct and rectangle as area method or function on this struct. And yeah, the moment we compile this code, actually the rectangle implements interface implicitly. So we can work with that. You can create a function that accepts geometry as an argument, and you can actually pass rectangle into this function, and the compiler will ensure that this is actually correct. Although otherwise it would not compile. As I said, small interfaces are very common, and actually what's also common is so first, small interfaces, that's a huge thing. It's something that the GoLang community and GoLang authors are proud of. So yeah, I/O is always like a pain, right? Basic library I/O. And here we have a reader interface that actually, to implement a reader of any kind, it can be disk, network, whatever, zip file, you just implement one method. That's all. It's called read, and you give it a buffer of bytes, and it returns you amount of characters or bytes that is being read, and error, optional error. And of course, there are also other interfaces like read add, so that implements a seeking, but that's a different interface. You don't need to implicitly implement that. And you may ask, like, why? Okay, so that makes sense, but why the read interface, read method, doesn't return the slice of bytes, the buffer? So it could actually return a number of, it could actually either return buffer or, return slice or like array and amount of bytes read as a return value. Well, it's actually, again, it's a clever design decision, is that this actually can be optimized by the compiler. So if you do this, if you define a function that returns, allocate some memory and returns it, the compiler sees this as there's a term I forgot, as memory leak. I think it's not a memory leak. There's a different term. Anyway, it needs to create the structure, the buffer on a heap. And that if you create something on heap, you need to track it down. And when there are no pointers or uses of that memory, you can using garbage collection, you can clean it up. However, if the read function is written this way, so we have a buffer, you create a buffer first, and then you pass it to the function. When you create a buffer, you can actually you're in the context of some function. Compiler can actually ensure that this, if it doesn't cease the buffer to leak to a different context, it can actually create the buffer on stack. And stack is a much more efficient way of allocating memory. Just you have a thing called stack frame. Every method or function creates a new frame, and all the variables are there. And if you return from a function, that stack pointer goes up or down depending on how you see it, and the stack frame is freed, and there's nothing like memory garbage collection there. Just local variables go there, and yeah, so that's nice optimization. So that's why sometimes you'll see that you're passing things into functions, whereas you could actually design them in a way that the structures are allocated and returned instead. But in that case, it's more efficient to do it this way. Here we have an example. So we have a reader. So it's actually a string reader, but it can be pretty much anything, read a file or something. And then we create a buffer of 4 bytes. And this can be created, actually, we actually know that this is a structure of 4 bytes. And that's the underlying implementation of a slice. This is a slice, but underlying implementation, eventually it uses array, right? So it's array, it's a fixed array of 4. And there's some magic in the make function, built-in function, so the compiler understands this. So it can actually, there's no guarantee, but it can actually, and we will try to allocate this on the stack. And as we read the data from the loop, it will just reuse the buffer, like it's on the stack. And then when you exit this function, it will exit. So that's just a departure from my talk about interfaces. So yeah, embedding is also possible for interfaces, not just for structs. So here we have interface, which is like read writer, and a type is read writer if it implements both reader and writer. So I expect that in the writer interface in the standard library has a single method called write, and that's so you have this like implicit implementation of interfaces. So interface assertions or type assertions. In Ruby, we have several helper methods on objects. These are defined on all objects, like if object is of some particular class, or we have a respond to, which is very common in Ruby, if an object responds to method. So if it quacks like a duck, it's a duck. And we have these in Go as well, and these are very common in Go. So we have var x here this is called empty interface. In 1.18 you can actually write var x any equals 7. And then we don't know what this actually is, although we see it's set to 7, but maybe this is coming from a function from our library which returns an empty interface. So we need to actually do type assertion, like we want to we want to ensure that this is int. If it's not int, then the compiler will write an error. And there's other thing and other syntax. If you use this type assertion in the context of 2 variables, t and ok, here it will return, I think it's Boolean. I'm not sure if that's error or Boolean. Okay, I think it's Boolean. So if that's true, then you got an integer. So this runtime value, which you don't know during the compilation, was actually or is actually integer. So yeah, and actually this is very common in Go. So we have a syntax called type switch, where you can actually like use this syntax to actually find a type of a particular unknown or empty interface. Note that this is only available in switch block. You can't do this. Like there is nothing like an if statement. You can do if, but it's not like a built-in. It's a switch. So Ruby, we have at least four ways of doing loops. This is like the overall slide. In Go we have just 4, and it has also 4, like, it's just the same keyword but 4 ways. The first one is like C, C++, so Java or C#, typical like iteration. Then we have like while kind of syntax. We just do write for, and then we have a for, like empty for, which is like a for true, for always do this, like until break. And then we have a special syntax for with range. Range supports arrays, slices, strings, and maps and channels. And it's always like it always returns 2 values. The I is iteration, like a number, and the V is the value. That if that's slice, if that's a map, that would be a key and value. And if you don't want to use any of these, you just use underscore. You have to use underscore because that would be, again, compile error. It would say like, you're not using this variable. Why are you declaring? So if it's similar syntax, I'd say. In Go, you can actually use brackets, parentheses. I mean, you just don't do it. I think if you do it, compiler will complain. Of course, you do it when you need to do, like when you need to like to ensure some priority. But if you just have a expression, you must not to use parentheses. So what's very common with the if statements is like doing like assignment within an if statement. And it's very common in Ruby, and in Go you can do that as well. And even the type inference works the same way. You can use a semicolon within the if statement to actually test for the value, and it's very common. You do this all the time within Ruby, within Go. And of course, variable is scoped to the block of the if block. Switch, it's like in Go, it's like in C, except the Go only run through the selected case. So like there is no fallback, and you can use break, but you don't have to use break like in C, for every single case. So it's like a natural. The moment you write your first switch, you'll understand. So enter Ruby. This is not common pattern in Ruby. Like you would probably use the block version of the open method, but you can ensure that something is called. So this can be done within Ruby. Again, as you can see in Ruby, you can do several things in a different way. In Go, we have differ. This is special built-in function, and you want to use it this way. You're opening a file, then you're testing for error. We'll cover that in a minute, and then you're returning. So you're entering differ will call this close method at the end of the block of the function. Let's say. Sorry, function, not block. I think if this is in a if statement, it will return only when the function returns, which is very handy. One thing though I've encountered with a blog post or video that was stating that close may actually return error and differ ignores errors. So it might be not a good idea. I'm not sure. I really like this syntax, so I have never seen a close to return error in my life, I guess. I'm not sure, but it can happen. Yeah, so just be warned. I'm not sure what to take from this, but differ is not only used for closing, but you can do and get away with other things, and also we'll see in a bit that it can work with panic. Comparison, so in Ruby, it's a mixed bag. It's similar to Java, C#, and a lot of other languages. You have like several equality methods and operators are like object equality and contents equality, and optionally you have hash methods if you want to put things into hashes. And you need to, like, when you're doing this, you very often, you know, like the probability of doing this incorrectly is really high, and even experienced engineers will just not understand either, or will not implement everything that's really needed. And then the moment you're starting putting things into hash, you know, crazy bugs and hard to track them down. Go again, that's a nice difference here, is like it solves the problem completely by the language says like two interfaces or types are comparable if either interface value is nil or the underlying type is the same and comparable, and it specifies comparable types. So pretty much everything is comparable from the built-in types except slice, map, and function. In case of struct and array, if all the fields or elements are comparable. So that's comparison. Now, hashes are implemented like there is no hash function, and you don't. So first thing is first takeaway. There's no equal question mark methods or functions in Go. You just types are either comparable or not. You just can compare or not, and the compiler will tell like this. You can't compare this. Sorry, that's like not comparable, and the compiler will know. It will tell you. So it's pretty much problem solved here on this front. And then we have the hash problem, which is again doing this right is not easy. And the way it works is like you can only hash comparable types, and if something is not comparable, you just you need to explicitly create hashing functions and call it. So if you have a k variable, which is perhaps maybe it's a map, well then you create a method hash key that will return, let's say, integer, and that one can be used. Or you can optionally use some kind of a primary key if there's maybe a structure which has some incomparable variables or fields, then you can do that. There are some utilities like cmd equal, reflect deep equal, which can help you with some equality conversions, but it's good that this is explicit. It's good that you have to use these special functions, because then, you know, when you're facing a problem, you'll like clearly need to research that and, you know, implement it in a way that it works. Exceptions, big topic indeed. So in Ruby, we have exceptions, typical object-oriented program, just like Java and just like C# and other languages. And so Go don't have exceptions. Go has errors. And Go encourages explicit error checks at API boundaries. Although it has a built-in mechanism, there's a built-in functions panic and recover, so you can actually mimic exceptions. You can actually use basically panics, and it works just the same way as exceptions, and it starts to, you know, rolling back from the stack, the call stack, until either you have a recover, and it's not a block, it's actually special again function. And you can use only recover within a differ block. Or if there is no recover, it will exit, like the program will panic, which will like exit process and show you the error message and all this call stack. So yeah, brace yourself, Ruby developers, because error checking is explicit, and you'll do a lot of error checking within your Go programs, and it's not a bug, it's a feature. So here is how it works. So we have this is, I think, from the standard library. Temdir creates, I think it generates a random, it either creates a temporary directory or just returns a temporary name, I'm not sure. However, it returns a name and error. So you call the function. If it's in the IOUtil package, and then you need to, and then you have the dir variable. We're using type inference here, so like it's a string, and compiler will ensure that dir is a string, and ensure that if you're passing it along, that it will be checking that. And then error is an error. Error is a special type, and if it's nil, then it's okay. There was no error. If it's not nil, then there was an error during the call, and you need to do something. And this explicit checking forces you to do stuff. And what's a big issue with programming languages like Java or like Ruby, like C# is, although in Java there is approach, there's also explicit checking so they are trying to solve this. However, in Ruby you don't have that. You just and that's like from experience. Programmers only program for the good path, for the success path. And if there's error, just like error, there will be an exception, and it will bubble up until you either catch it, and so the error will be like logged into the logs, and the request will be cancelled, or it will actually crash the program in the worst case. Here you actually are forced to think about it, like, so what I'm gonna do, like, what if temp doesn't, you need to think like, so okay, I don't have a temp directory, so do I need to stop the program at this point? Or maybe I can, what if, so okay, if that doesn't work, I'll maybe use /tmp. Maybe that's what I can do, right? So you need to think about it. So yeah, that's how you do it. Again, the if statement, as we were talking about previously, you can do semicolon and check for the error immediately. So it's nicer. It's just a single line, basically 3 lines, but it's nicer. And you will do this a lot. So with errors, you have a problem of redeclaration, reassignment. So here we have a variable that's been declared, and you actually and you will run into this very often until you like get familiar with this. So variable may appear even if it has been declared, if it's the same scope assignable, and there is at least one variable that is created by the declaration. So I know this is a mouthful, but what it actually says is, what I'm trying to say is, we call open from the OS package, and it returns f and error. Okay, let's skip error checking here for now, and then you can also, like, the compiler won't enforce you to do the if statement, so you can actually ignore the error. You can even, I think, write underscore, and that's like, don't do that, please. Anyway, and here we have a second line where we call fstat, and that call also returns another variable d and error again. And the above, this example is legit actually, because normally, like, the error, if you think about it, is like you are declaring f and error on the first line, and then you're declaring d. It's okay, and error again, but error was already declared in the previous line, so that should be like compiler, like error is already declared. But for the sake of simplicity, because you'll do this a lot, compiler will allow this if those three assumptions are met. So D was already declared, so it's okay that error will be redeclared. So like, and it needs to be the same scope and assignable. But this won't work for single values. So we have a do something here function returns, and we are declaring n and error. Error is error, and then we do something again, another method which only returns error. We have a lot of functions in Go which just return error or nil when there was no error. And here you'll see that the compiler will actually tell you, like, no new variables on the left side of the assignment. And you need to solve this. The solutions typically, there are multiple ways, but the solution is typically like you declare error explicitly on the top of your function. You declare var error, and then you just use a normal assignment in the special case in the do something again call. Interesting and important thing is errors are values. So errors, you don't think about like them as exceptions or as like special, something special. It's just a value. It can be anything. It can be a number. It can be struct. It's very often a struct, or it can be string. So what you do with errors is like you compare. Typically, like from the IO package, you just when you read something, it will return end of file, which is a type and a number. So it's arrow type, and it's essentially an arrow type, and I think it might be string. I'm not sure. An error is a built-in interface actually, so it's a type interface, and this is how it looks like. It has a single method, a single function method called error, and this method or function returns string, and that's all. Like you can create your own errors. You just need to have a method that returns a string. So yes, we can create our own error. Like this is a path error. I think it's just from the standard library. I'm not sure. And it's a struct. There's some path as a string, and this is not error yet. However, the moment you declare error function, it's an error right now. From now on, you can use this as error. And what you should do is you should have some kind of maybe constants, so you can easily compare those errors. Although errors are values, checking for a specific type can be useful, and we have you can use this type assertion. So like in this case, it's switch. It's very common, or there are other things I'll talk about in a minute. Errors are all very often string based. So there is errors package with a new function which will create an error which is actually a string, and then it's just string. And in the years ago, what was very common to see in Go programs was actually scanning those strings for specific errors. Like maybe if you saw math, if an error starts with math, quote math, column. So then you do something like, it's a math exception. Please don't do that. You shouldn't do that. And there are no this was added in some early versions of Go. You have error wrapping. So there's error f in the format package, which you can use to actually embed error into error. And then there is a unwrap method, which you can call and get to the original error. So that's what you do very often with exceptions as well, wrapping exceptions. And once you have that, once you have implemented this unwrap, and again the error, like the error's new function will return wrappable error, error f will create such an error. There are two helpers in the errors package, is and as, which can help you with checking if for custom errors. So is reports whether any error in the error chain matches target. So it actually unwraps until it either matches or not. So it will repeatedly calling unwrap. Okay, and then there's as, which finds the first error in the chain that matches target. And that returns a boolean, so you can use this in an if statement. And it works similarly as, so it works similarly as. And these were added again some years ago. I'm not sure in which particular version of Go, but you can use them, and you should use them. Some libraries have this pattern that errors, like checking for errors, is so painful that in some contexts you don't actually need to check. Maybe you have some kind of maybe a script, migration script, whatever, And this there's a Go community pattern is that you prefix your normal functions which return errors with must. So we have an exec command which executes SQL statement here. This is coming from a real world example, returns a result and error, and then there's must exec which panics. Basically, if there's an error, it will panic. It doesn't ignore the error, but it will panic out. So basically, if that's a script, you can do that as well. So require and packages in Ruby, it's a big topic, and I think it's a big pain on a larger Ruby code bases. So there's this thing called load path, a list of array of directories where you require your files. And RubyGems, the packaging library, adds a ton of load entries into the load paths. Loading in Ruby is actually very slow because of the design of RubyGems or how it works. I was doing researching this years ago, how we could actually speed it up. There were some patches, but eventually it's still slow because RubyGems actually allows you to install multiple versions of packages, and it's not great. And so require is one way of requiring loading dependency, loading Ruby files. There's also load. There's also require dependency, and there's also require relative. And so it's a mixed bag. It's a lot of stuff. And within Ruby, you need to be very careful. You need to do this in a way that it's you can maintain the code base for a long time. So we don't have any kind of concept of packages. There are RubyGems, which are libraries. So collection one or more basically source files. And what's typical is that you have a lib subdirectory, and then within this you have mylib, and then you package this as RubyGem, and then you have all the requires there. And then in the web application, you just require the mylib, and it will require all the files. But nothing is enforced. You can name the library, name the directory, anything, and the subdirectory doesn't need to be 3, as in the mylib /3. It can be anything. And the modules and namespaces within those files can be anything. Again, it's free form, do whatever you want to do. For this reason, navigating large code bases can be difficult if you're not strict about this. And turns out that a lot of projects are not strict about that. And guess what? Our project is totally not strict about it. The Ruby on Rails tries to solve this with auto-loading. It's a long standing pain. We are just migrating to the latest version of the auto-loading library called Sitework, and again, it's a third time we're migrating to a new auto-loading, and it is what it is. Like Ruby was designed as a scripting language, object-oriented, and it was not like built with Ruby on Rails in mind. Nobody, the author Matsumoto, had no idea that there will be Ruby on Rails actually. In Go, we have packages, and package is a directory, it's an important directory on your operating system with one or more source files, and these are compiled together, and it's either binary, so you have an executable if the package name is main, or it's a library, it's like a package if that's not named main. Imports follow directory structure. So if you have a net package, it needs to be in the net directory. And I just love that. It's so easy to navigate things. You know where things are just by looking on the imports. Okay, and this is just the beginning. It's more than that. So unused imports are not allowed. So if I import fmt and net, and I just use net, the compiler will say like import is unused. This can be a little bit, annoying, but Go community built a lot of, a lot of these things and tools are shipped within the Go itself, like Go format, Go fix, and things like that. and you can very easily integrate it with any editor of your choice. You don't need even have plugins. You just bind a shortcut to Go Format or Go Fix and things like that, and it will fix all the things for you as you type the code or as you save. So here, if you really want FMT, and FMT to be imported all the time, maybe you're doing some debug statements. Again, you can use printf, the built-in function, but if you don't like that, you can actually work around this by writing like var underscore, import underscore FMT. There's some kind of a syntax problem on my slide here. So what you can do actually, what you can do is you can write var underscore FMT something, and so you actually use the FMT, and then, from now on, the compiler won't complain. Hopefully, okay, this slide is good. I was worried about getting slides, breaking slides at this point. After how much minutes do we have? We still have some time. Are you still with me? We're almost done. So yeah, if you want to import something that's not gonna be used, like for example, this is a Postgres SQL driver, you just do import underscore. That's what you want. And the compiler won't complain that you're not using PG. Now import, the package names are actually namespace. So you don't want, like, if I have a package called CPU, but probably thousands of other people would create a package called CPU, and we could use it. And if there's a name clash, there's a way to work around this. I'll show you in a minute. But the import is like a namespace. Maybe like in Java, if you remember, that's how you write com.redhat.project name, and that's also a namespace. But here it's actually also a URL, and it's actually, and there is a mechanism that if you have import like github.com/lzap/u microfactor, if you import that, it affects a CPU package, and then you go do a go get, it will automatically resolve this dependency, and not only resolve that, it will actually, the Go tooling will actually download the package and build it for you. So you actually it works out of the box. Now to use package, you the last element of the import path /CPU. The CPU is the actually name that you want to use to access this package. So all the functions, all the types within this package, which are exported, this is important. Exported are only those which start with capital letter. You can use them. That's how you use packages. If you have again a name clash here, we have a net and lzap mynet, then you can import this into a different a name. So you create a import alias essentially. So Ruby gems, yeah, it's a pretty much nice concept within Ruby, although the performance is not great when you have many of them. Ruby DSL, here is an example how you have a Ruby DSL. A little bit of DSL, not too much complicated, yeah, that's how you create dependencies, and then you use a thing called bundler, which is a library or CLI program that manages dependencies through the whole lifecycle of your project. You create a file called gem file, and then you specify libraries you want to use, and equals specific versions or higher than specific versions and things like that. When you do bundle install, the bundler will create a file called gemfile.log, which will actually essentially lock the file versions. And then if you commit this into your Git directory, Git SCM, you're actually ensuring that the whole team is using the same versions. A couple of problems with that. First, if Ruby gems is down, you can actually resolve these and install these, which is an infrastructure problem, not a language program, but actually Go solves that. And second, not all projects can afford, committing a log file. Our projects actually don't do that because we actually build all the Ruby gems into RPM packages, and then we maintain the versions we want. And in that case, it doesn't really work well. And there is also another problem which I'll describe in a minute. So with Go, you have these modules. So if you do go get, it will automatically find all the imports and go and find all the dependencies. But it works a little bit different. We'll be talking about modules in a bit. Modules are essentially like a set of packages, similarly to Ruby gems. But Go here, there's a difference. Go prefers older versions. Dependencies must be explicitly bumped. So if we have project A or dependency A, which needs C higher than 14, B needs C higher than 16, RubyGem will actually pull version 1.16, the latest and greatest, the C dependency. However, Go will actually pull the 1.14, which is the oldest one, which is not the latest and greatest. And that's for a reason, because here, when C, author of C, releases a new version, 1.18, well, RubyGems pulls 1.18, automatically. And this can actually break your program without actually you knowing, unless you're using log files. And even if you're using log files and you do bundler update, this will be like unexpected, right? Hopefully it works, but there might be problems. Whereas Go pulls 1.14 still until you actually tell it to pull 1.16. So we have a module, which is a collection of packages which are related together, or doesn't have to be, but there are usually. And we have a new tool called GoMod. This has been added only recently, a few years ago, I think. And before that, there were several like packaging projects. One was actually shipped with Go called Deb, and others. But this is now built in the language. And first, if you want to create a new module, you do GoMod init, and we'll create a short file called GoMod, which contains essentially like the module name and the required Go version. And then it will also, if you already have some sources with imports, it will automatically detect those. And since imports are actually URLs, it will figure out those URLs. The Go module and Go get understands the URLs, and if that's a Git, it will actually go and get the latest tag within the Git, or if that's a subversion, it will do the same regular. And then, of course, if that's just a regular URL, if that's not a Git, there is some kind of HTTP metadata headers or something like that can actually fetch metadata from those. So you can actually write services that will provide you packages, things like that. There's a new feature of 1.18. If you create a Go work, it essentially like overrides Go mode, which is great. We are using this in our own project. We have a gem file local, RB I think it's called, where you just define your own plugins and stuff and things like that. And then once you have the Go mod file, you just do go get, or go get do U means update, like update to the latest versions. And there's also go mod tidy, which cleans up the Go mod file, remove dependencies which are unused and things like that. Go maintains also a Go sum file. This is automatic, but you want to commit this into your Git. And that's for like infrastructure when something goes down, or security and infrastructure. So these are cryptographic hashes of the source files or sources. And if someone would actually like modify, took control of the remote GitHub repository maybe and put some malicious code, this would actually show the Go mod tool actually figured out and show you that there's a problem. And also there's one more thing. There's some kind of a proxy which by default Google is running a Go Go service of some kind that helps you when things. It maintains those hashes as well, and it also I think can act as a proxy when something goes down. It can help you to download those packages, those dependencies. It works. It's something like an internet archive, but just for Go modules and packages, which is great. And you can actually run your own, of course. I'm not sure if it comes with Go, but you can easily run your own Go proxy. So you can, and this is a standard practice. Again, a lot of things in Go are not inventions. Some of them are, but a lot of things are just, the way we work today. It's been built in the Go, and you just use it. It's just pretty natural. So to install modules, you just git clone. Typical, if you have any kind of software library, you do git clone and go get, and then you can just go run or go build. It will automatically work. There's a special syntax //.. where it will do import detection, and I don't want to go into details, but sometimes you want to do that on projects which are not actually modules yet. So this will actually get everything you need from the whole project. So yeah, encapsulation in Ruby we have private and protected keywords or special things. Again, in Go we have exporting, as I said, capital letter. Now there's no concept of sub-packages, so there's nothing like protected. So if you have x and x/y, that's not a sub-package, that's a different package. It lives within x package, but it has no benefit. There are no benefits from being a sub-package or being sub-directory in a package. Concurrency, it's a mixed bag in Ruby. It has a nice suite of libraries, like Ruby concurrent is very nice, a lot of patterns, but the problem with Ruby is that the stack suffers from the GIL, the Global Interpreter Lock, and scaling of Ruby on Rails application. That's not great. You typically run a lot of processes. You are trying to take advantage of copy on write on Linux, but eventually, Ruby is not great in returning memory back to operating system because of fragmentation, and this is actually really good in Go, and they're trying to solve this. They know about these problems, and they were trying to specifically avoid a lot of design things and design decisions in the Go runtime, where to avoid memory fragmentations. And a recent version of 1.18 actually more aggressively returns memory back to the operating system, which is nice. It comes automatic. You don't need to do anything. And we tried also things like JRuby and on our project, but we have so many dependencies, it didn't work well. Concurrency goes completely different. It's like different world and different design. Everything is different. It's because this language and this runtime was built at Google for actually writing specifically services, HTTP services, multi-concurrent services, networks, daemons. And so in Go, this might come as a surprise for you, is you can't create a thread, operating system thread in Go. Well, you can if you have a Go C Go library, but in the runtime itself, there's no concept of threads. Instead, we have a concept of Go routine. Go routine is a lightweight thread. It's managed by Go runtime, and it's also known as the green thread, and Ruby does have that. It's not a novel idea, but what's novel is really enforcing you in this world of Go routines and taking all the hard work for you. And the Go runtime will actually schedule those Go routines on one or more threads. And typically, if you run a Go program, it will spawn one or more threads when it's needed, up until n CPU cores. So if you have 10 CPU cores, it will create up to 10, maybe 10 plus 1, I'm not sure, threads, and it will schedule. There's Go schedule. We will do a lot of optimization. This is like really, there are a lot of talks about this, how this works. It's crazy. Locking, even, for example, how locking works. Sometimes like you want to do a few cycles before you actually sleep the Go routine, because maybe if the wait is not long, you can actually immediately take the data. Things like are crazy. And you don't have to do anything about that. Like everything is automatic. And what's interesting is the first version of Go 1.10, even 1.1, I'm not sure, had fully concurrency, like implemented was fully concurrent. So Go routines were there, everything was there, but everything was running in the single thread, because they knew that the design is good, and they will add threading and parallelism later. Concurrency is not parallelism, by the way. Nice quote by Rob Pike, nice talk on YouTube. I highly recommend that. So yeah, how you create a Go routine? You just use keyword Go, and then you pass a function. This function will run in a Go routine. How Go routines talk to each other? Well, you can use the normal way, like you have a shared memory, maybe a global variable, and then you create a mutex, like a locking mechanism. So you can't really access, you can access a single memory block or a variable from multiple Go routines, but it will lead to eventually to problems, right? So you want to use the locking, so you have mutexes for that and other things you would expect. That's all in. However, GoLang programmers are encouraged to use channels for communications. Channels are essentially like pipes. You can think about maybe variables or pipes, depending if the channel is buffered or unbuffered, and it's synchronized. So basically, channel has a type. You create channels via make. So you do make, chan, and the type. And if you also provide a number, that's a buffered channel. Unbuffered channel is when you put something into channel, and you pull something from channel. And the syntax is using this arrow to the left side. I'm not sure how this is called. Channel operator, channel receiver, maybe. So the first function writes 1 to the channel, and then it closes the channel. Also, that's why the built-in function closes for closing channels. Okay. Once they are done with the channel, you close it. You want to say, hey, I'm done. I'm not that was the last bit. I'm not sending anything else. So the receiver, which is again another Go routine here it just stores the variable, stores the integer into a variable, and then that's it. But typically you have some kind of loop when you're waiting for data, and then once it's closed, there's a special thing to detect some that the channel was closed, and then you just finish your job. What's important to understand is channels are can be blocking. For example, if you have buffered channel and you have 100 here elements, the moment you store 99th and 100th integer, it will just work fine. It works like a buffer, but the next 101st integer, it will actually block. The Go routine will be blocked and won't proceed until something else. Other Go routine will pull values from the channel. So that's how buffered channels work. So there are several ways of receiving from channels. You have range and you have switch. This is actually from my microfactor Go project. So yeah, we have. It's basically a factor, collect some facts from about hardware, about operating systems, and those run in parallel. So it's very fast. So I have a two close variable, how many reporters are there. And then in range, I'm spawning those reporters as Go routines, and then I'm waiting in a range. Again, I'm in a range, I'm waiting until all the data comes back, and then if the channel was closed, I close that, and I'm done. So yeah, although channels are extremely good and extremely a good fit for the if you're writing services, if you're writing HTTP servers. Basically, previously in Java, C# or Ruby, you have probably you spawn some threads, and then you have some kind of a thread pool, because you don't want to spawn many threads, because threads are kind of expensive. These are not processes, not as expensive as processes, but they don't scale well. If you create thousands of threads, you might run into memory issues and things like that. So you end up with a thread pool. You have like a pool of threads, and then you have some kind of queue. And as the requests come in, you enqueue in the queue, and then from the from the thread pool, you are just processing those requests, and that's how you basically work. That's the traditional approach for writing server-side or HTTP servers. Of course, there are eventful things as well, but this is one of the approaches you can take. With Go, as like you don't need to solve this. You just, for every single connection, you create a new channel. New Go routine. And because Go routines are really cheap, it's much cheaper than Thread, because OS Thread by default in Linux, I think, creates megabytes or maybe 4 megabytes of memory for the local variables on stack. Go actually uses a very nice technique of, it creates the local thread local memory portion much smaller, and then it kind of reallocates that as you create more and more local variables. It's like it's very interesting. That's a novelty, I think. So don't overuse channels as well. Meaning that if you can maybe sometimes when I was starting with Go, I was like thinking, oh, this is so powerful, I will put everything into Go routines and channels, and then the code can be a little bit less readable. So we like think twice about it. What's the added value? And take care when we're passing pointers. Of course, if you pass pointer to the channel, then you can, of course, run into issues, right? Because you're changing the same data. You could be changing the same data. So that's with the concurrency out of the way. Final notes that this is actually what I want to say is in Java, C# or Ruby, to create a performant HTTP server, you need to do a lot of stuff. With Go, you just here's a fully functional production ready server that is on 4 lines, and it can handle thousands and thousands of concurrent connections. And it does this by creating a lot of Go routines, and the scheduler will handle all of that for you. You don't need to worry about threads. You don't need to worry about maybe running multiple processes. Like, sure, today we have containers, so you probably scale in a container because there are some limits, of course. I'm not saying that the Go program will handle infinite amount of requests. That's not the case. You have some constraints. You have memory, you have a CPU, but an I/O. But overall, that's a great thing to have. So with that, let's move on to memory management. So again, as I said, so Ruby has uses pretty much everything, a heap for everything, and the implementation suffers really hard from memory fragmentation. There has been some improvements, but it is what it is. For large projects, you need to think about how you deploy your application, and operations is probably a challenging task. Go runtime has a modern garbage collection, and it has optimizations. It's been, the library has been designed to optimize, to allow that the compiler to create as much memory, to allocate as much data on stack, which is much faster. You don't need to actually implement garbage collection on stack. And for the rest, for the heap, there's a concurrent mark and sweep garbage collector as well. So you don't need to actually worry about that, but of course, don't allocate a ton of memory if you don't need it. And yeah, there's also a package and can have, or actually Go file can have initialization function, which can be used to initialize maybe a package. So maybe you want to allocate some memory. This is used in the standard library quite a lot. So it's kind of a constructor for memory, for packages. Metaprogramming is very common in Go, in Ruby. So yeah, define methods. There are a lot. There are books about metaprogramming, and you can do a lot of stuff with actually writing code in Ruby. You extending yourself. It's really powerful, but again, it's a little bit hard to navigate through a large code base when you are using that a lot. And Ruby on Rails, it's built on metaprogramming. It's like it has in its design, its configuration by convention, which is okay for the small projects, but for a very large project, I think it can be sometimes painful, or definitely it's painful for newcomers who want to just fix a bug, try to navigate, and you need to learn a lot of stuff before you actually can navigate. Go has an answer. Don't have, of course, there's no metaprogramming in a Ruby sense in Go, but there is an answer that's called generation. Go generate is a built-in tool, and developers can actually implement their own generators easily. Like for example, if you have those iota, enums, constants, there's a stringer Go generator which will create helper functions that will allow a function that will allow you to convert from the strings to the constants, or there's like SQL generators, struct and migration generators, and many more. So code generation is a solution. It is like, be prepared to generate some code with Go. It is in the end compiled language, and compiled languages very often use this technique to work around some issues and to remove boilerplates. What's nice about Go is that it comes with a lot of tools. This is like not a unique feature. However, it comes with a ton of tools which are typically like not part of a language. Of course, building, running tests, okay, that's what you have, but formatting code, static analyzer, and then module dependencies. These days, modern languages do have that, and document generation as well. And there's also like renaming, like refactoring tool, which can help you with renaming. And what's great is that this formatting tool, which formats code into like the standard format. Everyone in the Go community agrees that they don't like it. Like they might be things that they would do differently, but they like the fact that there is such a tool, because if you rename a variable using Go rename, then it will automatically ensure that the Go source is formatted. So you never are running into huge patches which are just changing white space and things like that. And what's also interesting is that there's Go PLS, which is a language server, which integrates with IDEs and editors like Vim, Emacs, and VS Code. And this, I think, also comes with Go by default. I think it's one of these extended libraries, which maybe it doesn't come. It's not in the core library, but it is in one of these extended libraries. And that's great is that you don't need to install other tools. Everything works out of box. Just install your VS Code plugin or Vim, which is, by the way, there are two, Go Vim and Vim Go, and Go Vim is written in Go, while Vim Go is written in Vim. So I'm using the former one. And it works just fantastic. You don't need to install pretty much anything, and the language server somehow works automatically. So this is great. Now 118, a lot of things, big feature, parameters proposal are also known as generics. There's test fuzzing, any alias for interface, empty interface, comparable. Go format is now faster because there are two important things. That there is Go space format fmt, which you give it a package or project and will format everything, and then Go file fmt, which is a smaller tool, well, a tool that works on a file level. It's like a file level tool, and is now faster because the Go fmt with space was doing things in parallel, while Go format was just a single Go routine. It's now being improved. Also, there's a big change is that it is new package net IP address ADDR, which is much more efficient and it's also comparable than net IP. So it's a big change if you're writing anything that has to do with IP addresses, which is pretty much these days all the code, right? And that's a big change. But you can still use it's a non-breaking change. Net IP is still there, but a lot of functions will perhaps there will be some translation, so you'll have some functions that will convert from IP to others and vice versa. And I didn't want to go into generics, but I just want to share how, when I saw this proposal, I was like, I'm not sure. I like Go because it's free of these complex things. I'm not sure. And GoLang team was actually, they had a lot of proposals and they had a lot of iterating on how to approach generics. And the final version, which is now in 118, and by the way, the language is now ready, and they will be gradually improving the core language library, the standard library with type parameters, with generics in the future versions. But the language is ready and you can start using it, and they want to learn first. They don't want to just start away refactoring the library, of course in a compatible way, but maybe there's something missing. So they want to wait until things settle down. And this is the syntax. You have square brackets. So after your function name, you have square brackets where you define the types. So you just use identifier like in T in this case. And it can be int 32, int 64, and float 32. And then you, within this, within the context of the function, you can use T. And here, since the compiler knows that it can be either int or float, it will compile because s plus v, as we're adding something to variable t of type t, it's called s of type t. That works because we know the compiler knows that it's one of these, it's actually a number, right? It's not all the numbers, but it's a number. So you can then use the sum function with either integers or floats, and it will just work. And previously you would need to have some int, some float, like two functions in Go, and this the type parameters nicely solves this problem. However, one thing to keep in mind, to keep it simple, you can't actually mix and match type parameters. Like it's either int or float. You can't, like, it's pretty obvious here, like because the variadic parameter here, m, is of type t, which is kind of either be one or the other, not both. And since there is also type constraints, a new syntax you can actually define a type, and that is like you can introduce a type called let's say integer, and say integer will be int 8, int 16, int 32, int 64, and this will be integer. And there is actually a new package which is now in X, I think it stands for experimental, where you can there's constraint. There's a typo. It should be constraint, not constants. Constraint.integer, and this will actually, like, it's any kind of integer. and then the rest is the same. So this is how you, those type constraints, how you define them or declare them. So in the interface on the first line, not sure if that must be the first line. I think it must be the first line. You define like maybe, and this is from the constraints package which comes with Go. Ordered, for example, is integer, float, or string. So you know that it's ordered, so you can actually do equal, less, and things like that. And compiler knows that. That tilde is essentially, the operator tilde is for underlying types, meaning that if you create a type called myInt, which is int, and then the int without tilde would not match. But if you have this tilde, that stands for underlying type, it will work. So for example, signed, so again, it's interface that's in the constraint package, and it's like all the int or underlying ints that are int 8, 16, 32, and 64. And these are signed. These are, and there's also unsigned and things like that. There are two especially pre-declared identifiers, comparable and any. Any is, as I said, interface, the empty interface, because you'll use empty interface a lot in these type parameters, and so it's much shorter. Any is shorter. So nice change, and you can use this anywhere. And Go format will actually format all your code. If you Go format your 118, your code with 118 Go format, it will replace all the interface empty interfaces with any. And comparable is special identifier, which is essentially a list of all the comparable, which I talk about, everything except map and slice and channel is comparable. So we can use that, like you can have a function sort that will will have a type parameter, and t will be comparable. So you know that you can actually sort those. All right, we made it. Yeah, I know it was long, but I had a lot to say. So yeah, lots of links. Go ahead and go do the tour. And a couple of blog posts. I just used some examples from blog posts, and there's a ton of YouTube talks. Go ahead and watch these Rob Pikes, and there are other guys from the Go team and Go community, which have a lot of things to say. And Go documentation is really good. There's a blog, and there's also like a effective Go book. Also language specification. It's not probably you want to read, but you can sometimes find things there. It's written in a nice way. It's really readable. It's not like too bad. And yeah. All right. So yeah, have a nice day. Thank you.